Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads, determine the normal force, shear force, and moment at point C. Assume A is pinned and B is a roller. So we'll also say, and draw the shear force diagram and bending moment diagram. These I've just added. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Right, so we have a pin at A, so let's draw the free body diagram. So we expect to have two reactions at A. Let's call this as our A1, and then we'll have another one that we're going to call our AX, and then we have another one there that we're going to call our BY. Let's find out the this simply supported beam is loaded with two shapes of distributed loads. We have a triangular distributed load from A to C, and we have a rectangular distributed load from C to B. So we'll need to find the equivalent force for each one of the distributed forces. So let's start with a triangular distributed force. Okay, let's say we have our equivalent force here. Let's call this one is our F1. Okay, and this position, if you remember from centroids, this position is going to be equal to, from A, it's going to be equal to 2/3 of the length of the triangular distributed load, which is 3, which gives us equal to 2 meters. So it is 2 meters from A. That's where this equivalent force for the triangular distributed load is located. So this is just going to be equal to the area under the loading diagram for the triangle, which is just half, times the length, which is 3, times the maximum height for this triangle at this point. This maximum height there is 6. Okay, so this therefore gives us a 9. Okay, this is 9 kilonewtons. Okay, great. So let's find the distributed force, equivalent force for the rectangle. All right, this rectangle is it is located at just half the length of 3, which is just a 1.5. Okay, and this one is equal to F2 is equal to, this is just a rectangle, the area under loaded diagram, which is a rectangle, right? It's just the length itself, a 3, by the load itself, 6. This therefore gives us 18 kilonewtons. So we know everything about the load. So what we need to do now quickly is to apply the equations of equilibrium. So summation of forces about point A equal to 0 and clockwise being our reference. What do we have? We have F1, which is clockwise negative, so it's minus 9 times the lever arm, we said is 2. And then we have another one which is giving us a negative moment, which is 18 by, what's the lever arm? That's 1.5 plus 3, which is a 4.5, and then plus By times the lever arm, which is 6, therefore equal to 0. By is therefore going to be equal to, if we did the calculation, we have minus 9 by 2, minus 18 by 4.5, okay, and then this divided by 6. Then we have a 16.5 kilo Newton. Let me just repeat this. Minus 9 by 2, minus 18 by 4.5, and then divided by 6, 16.5. Great. So then we have to find the other one, summation of forces in the y equal to 0. Going up with our positive. What do we have? We have ay plus by minus 9 minus 18 equal to 0. So what is our by? This is our by here. This is our by, which we already found, and therefore our ay is just going to be equal to 16.5 minus 9, 16.5 minus 9 minus 18. So this gives us a 10.5 kilonewtons. Okay, a 10.5 kilonewtons. Great. So then finally we have the summation of forces in the x direction, which is just going to be equal to 0. We don't have any force in that direction, and therefore our ax is equal to 0. So let's replace this value. We have by, we said, is equal to a 16.5, and then we have ay, which is equal to a 10.5, and then we have ax, which is just equal to 0. Okay, great. So what we'll do is we're going to section the beam. We'll section the beam at C, which is at this point. So which section are you going to go with? Which section are you going to go with? I think I prefer the left section, which is rectangular, right? You can choose whichever. Okay, I could have picked any. I went with that one. You always pick which you think is easier. Alright. But being easier for the two, they just look more or less the same. But I've gone for the rectangular, the left hand side. So we have the left hand side. I've gone with the right hand side and the right hand side. So I went for the right hand side. Alright. So here I have a 16.5, and then I have this rectangular load. Alright, and then this rectangular load is a 6 kilonewtons per meter, and then its equivalent force, we said, is just going to be equal to, we called this one as our F2, and this one is equal to, we calculated it already, is 3 by 6, which is equal to 18 kilonewtons. We just said the area under the loading diagram. And this location is just, since this is rectangular, it's just going to be half the length of 3, which is just a 1.5. Alright, so here we have a shear according to a convention in that direction, like that. This point is C. We have the moment like this, MC, and then we have the normal force like that, NC. And then the short distance here to there, this one is equal to 3 meters. Alright, so we have all the information that we need. We can apply the equations of equilibrium. Let's start with moment. So summation of moments about point C equal to 0 and clockwise being our reference. What do we have? We have a 16.5 by 3. What else? This is anti-clockwise. And then we have a 18 by 1.5 clockwise. And then we have MC, which is also clockwise. And therefore, making MC subject to the formula, MC will give us, let's calculate. So we have a 16.5 by 3 minus 18 by 1.5. So this gives us MC equal to a 22.5 kilonewton meters. You can just check it. 16.5 by 3 minus 18 by 1.5. 22.5, yes. So found the moment at point C. So let's move on. Let's move on to find the shear force. So we have summation of forces in the Y going up in our reference. What do we have? We have a 16.5 and minus 18, then plus BC equal to 0. Great. Therefore, our VC is just going to be equal to, so we have 16.5 minus 18. So our VC is equal to 1.5. That's okay. It's equal to 1.5, which is positive, right? Kilonewtons. So 16.5 minus 18, 1.5. And then finally, we have summation of forces in the x direction equal to 0. We know there is no load in that direction, and therefore our NC is just going to be equal to 0. We have found the moment at C. Okay. Alright. And then we have found our shear at C. And we found the normal force at C. So let's draw the shear force and the bending moment diagram. So for us to draw this, we are going to use the differential equation that relates the distributed force to the shear force and the shear force to the moment. So we know that the rate of change of moment with respect to x is equal to the shear force, and therefore moment is equal to just the area under the shear loading. We also know that the rate of change of shear with respect to x is equal to the loading, and therefore our shear force itself is equal to the area under the load diagram. One thing I also need to make mention of is how the distributed force is related to the shear and how the shear is related to the moment in terms of functions. So if we have the distributed force as a function of x like this, okay, written as, let's say, coefficient a, just a coefficient a, x to the power n, plus other factors that are not written down. If the function that governs the distributed force is like this, then you expect the function that governs shear to be a polynomial of order, let's say it is going to be equal to b. Okay, it's going to be equal to b x to the power n plus 1. All right, and then the function that governs moment is just going to be equal to c x to the power n plus 2. I'm interested in the x to the power, these powers. Forget about the coefficients, these are just coefficients. And so we have the function that governs, so plus other factors plus other factors. All right. So there is always one step ahead. So if the shear is of the, if like in this case we have the loading governed by polynomial of order n, the shear will be governed by the polynomial of order n plus 1, and the moment to be governed by a polynomial by the order or by the degree n plus 2. All right. So quickly, let's start drawing. Let's this. Let's draw our lines. There we go for the shear. There we go for the moment. So this is the shear force diagram. Okay, and this is the bending moment diagram. All right, let me draw a line here like this. Great. Okay, so we have positive up, negative down, positive up, negative down. Right. Let's start drawing our shear force diagram. Let's start drawing our shear force diagram at A. At A, we have our initial value. Always we need to look at the boundary conditions. At A, we have our initial value of shear, which is positive, and it is 10 point. It is a 10.5 kilonewtons. So that becomes our initial value, okay? And it is positive. And then from A to C, we have a distributed force, which is triangular, equal to, which is negative. It's negative, and it is increasing. Okay. It's negative is 0 at A, and then at C it is minus 6 kilonewtons per meter. Therefore, you expect the slope of our shear diagram dV dx to also be negative and increasing. Okay, and this magnitude is just going to be equal to the area under the load diagram, which is just half times 3 times minus 6, which gives us equal to just a minus 9 kilonewtons. So again, I repeat, the load, the distributed load is negative and it's increasing in the negative direction from 0 to minus 6. Therefore, the slope for our shear will be negative and increasing. And the shear itself, the magnitude of the shear is going to be equal to the area under the load diagram, which is just half, since it's triangular, times 3, the length, times negative 6, which is the maximum load, which gives us negative 9. So the load diagram is a polynomial of degree 1. It's linearly increasing in the negative direction. Therefore, you expect moment to be a polynomial of degree 2, okay, which is going to be quadratic. So found minus 9, but we are starting from this boundary condition 10.5. So the two will have to interact for us to find the algebraic sum of where exactly the curve is going to end. So we'll have a positive 10.5 minus 9, which will give us 10.5 minus 9 gives us just a 1.5. So let's draw our curve quadratic from A to C. So it has a slope of negative and increasing. So I'll draw two slopes and then you choose for me which one you think is correct. Both of them that I'll draw will be negative, but I want you to choose whether it's increasing in the negative direction. So I'll have this one, I'll have this one. 1 and 2. Which of the two slopes has an increasing negative slope or a negative increasing slope between 1 and 2? Which one? Of course it is 1, right? Of course it is 1. Great. So go with 1. So let me just mark this boundary here. I mark this boundary. Okay. So let's draw this quadratic. We say it is coming up to 1.5, which is still positive. So we expect something like this. Right? Great. Something like that. Okay. There we go. So let's say this point here is our 1.5 kilonewtons. Great. So let's move on. And then from C to D, our load is equal to, our load is negative and it is constant. You expect the slope also for shear to be equal to negative and constant. And the magnitude of our slope is just the area under the load diagram, which is just equal to a 3 times negative 6, which just gives us a negative 18. Okay, it gives us a negative 18. Okay, it gives us a negative 18. So if the load is negative and constant, this is a polynomial of degree 0. So we expect the shear diagram to have a polynomial of degree 1, which is going to be linear and will have a constant negative gradient. So let's find the value, the maximum value, or the point where our curve is going to come to an end, or where it will end. So we have an initial value, positive value of 1.5, then minus 18. So if we worked out the two, so we have 1.5 minus 18. This gives us a minus 16.5. So let's draw our curve. We draw our curve. Okay, something like that. It's going to be a straight line. Okay, let's say up to somewhere there like that. Okay, something like that. This value here, like we said, it will have a negative constant slope. All right. So this value here, let's say is and the magnitude of this slope, we know it is already a negative 6. Okay. All right. So what is this value here? This value there, we say it is a negative 16.5 kilonewtons. Then the moment we reach at B, we have this load, which is positive, so the two will interact. So we'll have a negative 16.5 plus this reaction force, positive 16.5, which just gives us 0. It's important to always have a closure. There has to be a closure in your business. All right, so that you get your profit. We have closed our business. Okay, so this part is positive and this part is negative. All right, you need to mind about these points. We have this point here, which is 1.5. We have that point, which is a 10, and that one is a 16. We'll be mindful about this distance. Let's find this distance in advance. This distance, because we'll need to come and calculate it to help us find the maximum value of the moment, because we know that we have the maximum value of moment where we have shear equal to 0. So let's find that value quickly. We are just going to use similarities of triangles. Okay, we just use similarities of triangles and so on. So let's say we have a 1.5 plus 16.5 divided by the length, which is 3. Let's call this part x. And then finally we have just a 1.5 divided by x, and therefore our x is just going to be equal to, so 1.5 plus 16.5 is 18 divided by 3 is a 6, and then we have a 1.5 divided by 6, so this x is equal to 0.25. okay, so this x is equal to 0.25, right? Yes. So 18 divided by 3, we have a 6, then 1.5 divided by 6. Yes. So if we know that value, therefore we also know this value here, which is just equal to 3 minus 0.25. This gives us a 2.75. Okay. So once we have those dimensions, it will help us to do our calculations for our moment diagram. Then the other thing we also want to know is the equation that governs the shear, because we need to integrate it later on when finding the area under the shear diagram to find the moment. So let's find the equation from A to C in advance. So we have this equation here, Q, let's say Q that governs this line here. Okay, this line here will be governed by an equation. Okay, it will be governed by an equation Q. Writing it in terms of linear equations, we have Q equal to mx. Okay, mx plus c. Remember that equation, mx plus c. C is equal to 0, and our gradient is just equal to the change in height divided by the change in the horizontal, which is just equal to a 6 divided by 3x. This is equal to 2x. Okay, so if we made a section quickly of just a very small triangle, we just cut it at the distance x. If I write this, let me write the support. I'll have the support there, we found a 10.5. This is our A. This point here we say this is our Q, which we already found, and Q is equal to 2x. Then I'll have an equivalent force there of F. I'll have an equivalent force of F, and then this distance here is just equal to x. Then I have my shear V, and then I have my moment M. And therefore, summing up the forces, summation of forces in the y direction, we have, let's write what F is. F is just going to be equal to, F is equal to the area under that load diagram, just equal to half times Q, and Q is what? 2x, then times the length, which is x. So this just gives us x squared, right? And then summation of forces in the y direction, we have a 10.5 minus F, which is just x squared, okay, minus V equal to 0, and therefore V, which is a function of x, is equal to 10.5 minus x squared. Alright, so this equation is vital. Okay, so let me write this equation here. The function from A to C, our shear, okay, is equal to 10.5 minus x squared. Alright, can I wrap this? So we need that information because we need to find the integral of, or the area under the shear diagram for us to find the moment. So let's go ahead now from A to C. From A to C, we know that our shear, okay, is positive, okay, and it is decreasing. All right, it's decreasing from 10.5 to 1.5. Therefore, you expect the slope of our moment to also be positive and it will be decreasing. All right, and then its magnitude is just going to be equal to the area under the shear diagram, which is equal to integrating from 0 to 3 of our shear function, and our shear function we said is 10.5 minus x squared dx. This gives us, this is equal to just a 10.5 x minus x cubed divided by 3, and then we are evaluating this from 0 to 3. So this is therefore equal to a 10.5 by 3. Okay, let me just calculate this. I find the value. So this is 10.5 by 3 minus 3 cubed divided by 3. So we find the moment of 22.5 kilonewtons meter. Great. That is the moment at C. So let's draw our diagram. What did we say? We said the slope is positive and it is decreasing. Okay. So which of the two slopes are we going to pick? I'll draw two of them. The one like this or the one like this. Between 1 and 2. Which one has a positive, a decreasing slope between 1 and 2? Which one? Which one? Aha, I get you. It is 1, of course. We'll go for curve number 1. Great. Curve number 1 has a slope that is positive and decreasing. So let's go. And it is a polynomial of degree what? Polynomial of degree what? 3, of course, because shear is a polynomial of degree 2, which is a quadratic. Therefore, you expect moment to be a polynomial of degree 3. So it will go something like that up to there. So that's our point, and that point we said the value we found is a 22.5 kilonewton meters. And then, of course, that is not our maximum point. That is not our maximum point. We expect the maximum point to be at the point where we have shear equal to 0. Okay, so let's say this point is moving like this, like that. Okay, and then maybe I move this value because I will not be able to plot properly the other curve, which gives us the maximum value. So let me put it 22.5 kilonewton meter, like so. So that is the point. All right. So what do we have? We have this triangular load just at this point here from 1.5 to 0. Okay, let's work on it also. Let me just wrap this. Let's work on that one. Let's quickly work on that one. Let me just clear my little space. So what do we have there? There we have the shear, which is positive and is again decreasing. Okay, linearly, you expect moment to be quadratic. And then the slope for moment will be also positive but decreasing. And this magnitude is just the area under the load, under the shear load diagram. And this is just equal to half by the length 0.25 times magnitude of our slope, which is just 1.5. This therefore gives us that's 0.5 by 2 by 0.5 by 0.25 by 1.5. Okay, what do we have? We have a 0.1875 kilonewton meter. Let me repeat this: 0.5 by 0.25 by 1.5. Okay, so this is going to be quadratic, is positive and decreasing. Of course, so expect it to move like this, right? Great. We know now, and we both known. So let me come to this point like so. So let's draw a curve. This one is quadratic, so this will be our maximum moment there. Okay, up to there like this. All right. Okay, please, this one is quadratic. Think of this as this being quadratic. All right, quadratic, and this point here, this value here is positive, so we are going to sum it with a 22.5 plus 0.1875, and this gives us a 22.6875. So this is a 22.6875 kilonewton meters. All right, then finally we have, I'll leave the rest because it applies. Finally, from C to B, I mean not from C, from zero slope, this point zero slope, from zero slope, I mean from zero, from this point, what will I call this point? Let me call this point here is point D, where we have zero shear. So from D to C, I mean to B, from D to B, of course the shear is negative, and it is increasing in the negative direction. So you expect the moment to also be negative and increasing, okay, in the negative direction. And this magnitude is just the area under the shear diagram, which is just equal to a half times the length, which is 2.75, times the magnitude, which is minus 16.5. And then this gives us, let's calculate 0.25, I mean 0.5 by 2.75 by 16.5. So we have a negative 22.6875. So from where we are coming from, we have a positive 22.6875. They will interact. So we'll say a positive 22.6875 plus a minus a 22.6875. Therefore, this gives us 0, so that we close our moment diagram. The closure is vital again. So the shear is negative and increasing, linearly increasing. Therefore, we expect the slope to be quadratic in nature. Okay, but it will have a negative slope but increasing. Of course, we know that negative and increasing slope is just going to be from there. It is start like so, and increase. We may not have drawn it properly, but it will be quadratic in nature. Okay, I think this is about it. This slope here is, I mean this whole moment there, it is positive. Let me just clean it. This is all positive. And let's look at the value at C. At C, we found a positive shear 1.5, and we also found a positive moment of 22.5, which tallies with our diagram. I think this is about it. This is really about it, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, and continue subscribing. Bye bye, and see you in my next screencast.